Alright guys, we are going to start with the back of page 1 where you guys have the practice problems. So, how many of you actually took time and did your practice problems? 1? Oh my gosh. Okay, that's really sad. Alright, let's start out with Slim Jim. Slim Jim lifts a 40 kilogram object up 3.5 meters. How much energy does it have before it is lifted? How much? What is it? 0. Why is it 0? Why would it be 0? If it's sitting on the ground, why is it 0? It has no height. It's not that it's not moving, because objects up high cannot be moving. But since it's on the ground, it's got 0 height. Because remember, the formula for potential energy is mass times gravity times height. And if height is 0, that means potential energy is 0. All right, what kind of energy will it gain when he lifts it to the top of that mountain? Kinetic energy, not kinetic, I'm sorry. The movement is kinetic. It's going to gain potential. So it's going to take kinetic energy to get it up there, but it's going to gain potential to get to the top. Where does this energy come from? Who is moving it? Who? Jim. Jim is moving it. So the energy comes from Jim. It's not from magic. All right, calculate the box's energy after it's lifted. So what kind of energy is it going to have after it's been lifted? Potential energy. So potential energy is equal to, what's the formula for potential energy? Where can we find the formula for potential energy? All right, mass times gravity times height. So what is the mass of the box? 40 kilograms. Gravity? Yeah, we're lazy. Let's call it 10. All right, so 10 meters per second squared. And how high is it being lifted? 3.5 what? Awesome. All right, so 40 times 10 times 3.5. What do you get? 40 times 10 times 3.5? All right, 1,400. What units do we still have left here? All right, so our meters, we end up with 10 meters per second squared. We got kilograms per second squared. It's going to end up being a Newton meter, but since we're talking about energy, the unit that we actually use for it is the joule. So 1,400 joules is how much energy it is. If you forget about that, in your formula chart on page 3, it has Newton meters on there. Newton meters are joules, so it is present for you. Okay, number 3. If a car has 30,400 joules of kinetic energy, how fast is it moving? What kind of energy does it have if it's moving? Kinetic energy. What's the formula for kinetic energy? All right, 1/2 mv squared. So what is the mass of our, or actually, let's start at the beginning. Kinetic energy, how much kinetic energy does this guy have? 30,400 joules is equal to 1/2. Do we have the mass of the car?
950 kilos.
All right, 950 kilograms. And we're trying to solve it for, I don't even need that parenthesis, velocity squared. Do the little math. 30,400 joules, not 1/2 times 950. What is 1/2 times 950? It's 475. Okay, close. 475. So if we divide both sides by 475 kilograms, that's going to cancel this and all that out. Take this one over 475 kilograms. 475. Very good. 64 joules per kilogram is what we end up with. And then velocity squared. So the square root is 8. And if you work your whole units thing, whatever, you're going to end up with meters per second. I'm not going to get into that today. I'm more interested in you getting the numerical value. Okay? So, 8 meters per second. All right. Number 4. 6.5 meters. How much work did Slim Jim do? Did he do any work?
Yes, he did work. Yes, because he poured it.
All right. So if we have the box right here, the box weighs 10 kilograms and he's pulling with 35 newtons. Here's how you know he did work. All right, what is the formula for work? Work equals force times distance cosine theta. Now that cosine theta is actually kind of a big deal because that's going to show us whether or not we actually had work being done. Now what angle would we take of this? Where's the angle coming from? Here's what it is. It's the difference between the direction of our force. Now he's applying the force that way because he's been putting tension on the box. He's pulling it along. What direction is our box traveling? Also to the left, right? Force and distance. Well, what kind of angle is that? It's 0 degrees, right? Okay, do me a favor. Take the cosine of 0. Take the cosine of 0. Put it in the calculator. What is the cosine of 0? It's 1. All right, so we actually have work happening because our cosine is 1. They're parallel to, it seems weird, doesn't it? Because you think it's times 0. It's not, but cosine of 0 is 1. So what's the force being applied to the box? 35 newtons. How far did the box go? It traveled 6.5 meters. And then technically we would take the cosine of 0, which is equal to 1. So when you plug that into your calculator, what do you get? You should have roughly 227.5 joules. Newton meters. See? Newton meters. Excellent question. So why is the formula different on the chart than it is that I'm giving you here? I'm giving you the full formula, force times distance cosine theta, but on the chart it's just force times distance. On your exams, EOCs, end of courses, STAR, and everything, they're going to give you force problems where the force is parallel to the distance. That's a little bit of a different one then. You're looking at the kinetic energy and conservation of energy formula, I think. Well, that's our next topic. All right, but we just use the force times distance on those tests because it's always going to be 0 degrees. So, yeah. All right, so we'll always have 0 degrees, but in the real world, we have forces in multiple directions. So that's why we're teaching you guys a little bit more of a fuller way. All right, what kind of energy does the box gain? What kind of energy? Kinetic energy. And if there's no friction, how much energy does the box gain? Trick question. The box is gaining energy. How much? How much energy is he putting into it? 227.5, right? Very good. So how much energy does the box gain? 227.5 joules. It's gaining what's been put into it. Excellent, excellent. All right. I know we're going fast. We got a lot to cover. Besides, you don't want to watch a long, boring video later. Question 5. A 6-kilogram object slides down a frictionless 10-meter ramp. What kind of energy does it have at the top? potential energy. So up here, we've got potential energy. So there's 10 meters, 30 degrees, and it's weighs 6 kilograms. All right, so potential energy at the top. H must always be vertical. Calculate the H at the top of the ramp. Ooh, so H is what? You would think hypotenuse, but H at the top, height. All right, so we want to know what is the height of this ramp. How could we figure out the height? So, Katoa. I know, it's so ugly. It keeps coming back to us. All right, so if we want to figure out the height, we have to do SOHCAHTOA. So what do we use? So, ka, or toa? So, right, opposite over hypotenuse. So, S equals O divided by H. In the real world, that's sine theta is equal to the opposite. So, in this case, it's our little a, our height, divided by our hypotenuse, 10 meters per second. Our sine is sine of 30. So if we want to solve it for H, multiply both sides by 10 meters per second. And so 10 times sine 30, what do we get? 5. So my hypotenuse is, I'm sorry, not my hypotenuse, my height is 5 meters. Whew. All right, too many H's. All right, calculate the energy at the top. So what kind of energy is at the top? Potential. So what's the formula for potential? It's not going to take too long. You'll get these memorized. Don't worry. We got mgh. So what's the mass? 6 kilograms. Gravity is 10 meters per second. And now we know our height is 5 meters. So 6 times 10 times 5. 300 joules. Now, the evil thing that they're going to do to you guys on tests is that they're going to give you this problem, but they're not going to prompt you to solve it for height. They'll give you the box at the top of a ramp, the length of the ramp, and the angle that it is. You have to know, in order to find the potential energy, I need mass, gravity, and height. So you have to know that in order to find height, I have to use sine theta to get up there, the SOHCAHTOA. Sine equals opposite over hypotenuse. All right, so that's a good example of a two-step. They're not going to prompt you, they're just going to expect that you know it. Okay, what is the energy transforming into as it slides down the ramp? Yep, kinetic. So we're going from potential energy into kinetic energy. Okay, so looking at our next problem, number 6, we got a spring. A 3 kilogram object compresses a spring 0.6 meters, giving it 8.1 joules of energy. So we've got our little spring here. Box is 3 kilograms. Calculate the spring constant for the spring. What formula would we use to find a spring constant? Spring constant, what's one of our other formulas on the very front page? Potential elastic energy. My other class was starting to call this the Peel formula. P-E, elastic. Peel. All right, so what is the formula? Awesome, 1/2 kx squared. They're asking us to find the potential, or calculate the spring constant. They give us the potential energy. What was it? 8.1 joules was in our problem. We've got 1/2 times K. And what is K representing? Not kinetic. Go back to that front page. What is K? K. What is K? Spring constant. That's what we're trying to solve for. Why don't they use S and stuff? Because it confuses us with seconds or whatever. I don't know. All right, so we use K, and then X is the distance. Distance of what? The distance the spring was either compressed or stretched. All right, and so what was that in here? 0.6 meters. Now, here's the thing a lot of people forget. We get so hung up putting everything. It's 0.6 squared. Don't forget that. I forget it all the time. You don't. All right, so go ahead, work this one out. What do you get? What's it? Should have with 8.1 joules equals 0.18 K. And divide both sides by 0.18. And so you should get 45 is your K. And it's in Newton meters. Tricky part is knowing what formula to use when, and then it's just kind of a plug and chug sort of thing. Can we say that again? Can we just put J for that one? Technically, I guess you could. No, because it's newtons per meter. I'm sorry. It's not Newton meters. It's newtons per meter is your spring constant. My bad. Good question, though. What kind of energy will the object have when the spring is released? When you let it go, it's going to be kinetic energy. Awesome. It's kind of like 8th grade all over again, right? Potential and kinetic, but with more numbers. All right, number 7. So we've got a ball up here in position 1. Weighs 2 kilograms. If the ball has 120 joules of energy at position 1, calculate the height at position 1. What formula could we use to do that? What kind of energy does it have when it's sitting on top of a hill? Potential energy. What's the formula for potential energy? All right, so potential energy equals mgh. What is the potential energy of the ball at the top of the hill? 120 joules. So 120J. What's the mass of it? 2 kilograms. What's the value for G? 10. 10 what? Meters per second squared. And then we're solving for our H. How high up there is it? So, another plug and chugger. 2 times 10 ends up being 20. So if we divide both sides by 20, basically kilogram meters per second squared, divided by 20 kgms squared, 12 over 20 is 6. So this guy is 6 meters high. Seems weird. If you know the energy, you can figure out how high up it is. I know. What kind of energy does it have at point 2? All right, we have both kinetic and potential. The kinetic energy will probably be higher than the potential because it is losing height as it's falling down. And then where does the energy go at point 3? So here's 1, 2, 3, and oh gosh. What's about to happen? He's going to smush a little cockroach. What's that happening? What's it applying to the cockroach? A force. So, what's happening at the end? It is doing a little bit of work. It's applying a force to Mr. Squishy. And so long, sucker. Yeah, I like how y'all are like sympathetic to cockroaches now, but in reality you're like, ah, kill it, kill it, kill it. Okay. Number 8. Slim Jim carries a box for 6 meters at constant speed. How much energy does the box have? He's hardcore. All right. So, how much energy? What kind of energy does the box have if it's moving?
It doesn't have no energy.
It has kinetic energy. So, what's the formula for kinetic? 1/2 mv squared. So, we're solving for kinetic energy. So, what's the mass of the box? 12 kilograms. How fast is he carrying it? He's carrying it 3 meters per second. It's okay. So he's got the box, 12 kilogram box, carrying it 3 meters per second squared. Thank you. All right, I always forget that one. So what's our kinetic energy? You should end up with 54 joules. So 54 joules of energy for Slim Jim to carry it that far. Now here's kind of an interesting question. How much work does Slim Jim do? Work is force times distance cosine theta, right? Now here's the deal. We've got little Slim Jim. He's carrying the box. What direction is the force on the box if he's carrying it? What kind of force is he putting on the box? What direction? Up. So our force is up. My bad, I worded that wrong. What's the direction? Across, right? Horizontal? So my direction is this way. What's my angle between force and distance? 90 degrees. Do me a favor and on your calculators hit cosine of 90. 0. So work is 0. When the force is in a 90-degree angle to the direction it's traveling, you get 0 work. Which means like if you work at a cafe and you're carrying around food trays like this all day, and you're walking around like this, you know, whoo, I'm going to go bring you your food, you are doing 0 work. No work is being done. All right? But if you take your tray of food and you put it down on the floor and you kick it, now you're working. All right? Because now the force is in the direction of the movement. But when you're carrying it on your hand, it's not. All right. So kind of like a little trick question. No work's being done if it's just being held up. If it's at a 90-degree angle, nothing. He's going to be tired, but in physics land, he has done no work. So think about it, you know, like waiters, they get paid for doing no work. All right. 2 identical balls roll down opposite sides of a frictionless platform. Which one will be going faster at the bottom? 2 balls rolling down. Who's going to be going faster? Yay, they're going to go the same. All right, because they got the same potential energies, same force of gravity, same height. They'll actually be traveling the same speed. All right, last one, number 10. If the box moves 12 meters to the right, calculate the work done on the box. So we've got a box right here. The force is being applied at an angle, an 80 Newton force, and the box is traveling 12 meters to the right. So the direction of travel is this way. 80 newtons here. The angle between the force and the direction is 35 degrees. So what's our formula for work again? Work is force times distance cosine theta. So our force is 80 newtons. The distance it traveled was 12 meters. and the angle that the force is being applied for cosine theta is cosine of 35. So plug that into your calculators. I'm going to call it 4. 486.4 joules. All right? Okay. That concludes our review session. Now we get to move on to the new stuff.